Now let's continue from the last equation, which is equation 7 we derived in the previous video for the differential number of harmonic oscillator. We use that equation to find the average energy of harmonic oscillators. So if E sub t stands for the total energy of a system containing n harmonic oscillator, can then be obtained by summing over the energy of individual harmonic oscillator. From the total energy, the average energy per oscillator can be obtained through dividing E sub t over n in the form E sub average equals E sub t divided by n. However, Planck didn't follow this procedure. In order to catch the original idea of Planck, we will follow a different approach for the summation. And for that, let the entire XP plane be divided into elliptical strips of equal area. Note this, equal area. And I'm denoting these elliptical strips by numbers 0, 1, 2, 3, where 0 represents the center elliptical strip as shown in the figure. If H represents the area of a single strip, then the total area inside the nth strip can be written as A equals n times H. Using this equation in equation 5, we can write the energy of the harmonic oscillator in the form E sub n equals n times h nu, where again keep in mind H stands for the area of nth strip. Thus the change in energy of the harmonic oscillator on a given elliptical strip will be delta E equals E sub n minus E sub n minus 1. Substituting the values, we can write as n h bar nu minus n minus 1 h bar nu, which of course leads to h bar nu. The total number of harmonic oscillator n sub n in an elliptical strip with number n can be obtained by integrating equation 7 over the range of energy delta E. That is, n sub n equals n sub f times c sub 1 integral over energy delta E into exponent minus E sub n divided by kT times dE. At this point, we make an approximation, that is, in the limit of both h and delta E small enough, the integrand can be treated as a constant. With this approximation, the above equation reduces to n sub n equals n sub f times c sub 1 times exponents minus E sub n divided by kT integral over change in energy dE, which of course leads to n sub f times c sub 1 times exponent minus E sub n divided by kT times delta E. And I can re-express this equation as n sub naught times exponent minus E sub n divided by kT, where I replace n naught equals n sub f times c sub 1 times delta E, and stand for the total number of oscillator in the 0th elliptical strip. Using equation 8, the last equation can be put into the form n sub n equals n sub naught times exponent minus n h nu divided by kT. Now the total number n of oscillators can be obtained from equation 9 by summing over the total number of elliptical strips. That is, the total number n equals n naught plus n sub 1 plus n sub 2 plus up to n sub n. And if we substitute the value from equation 9, we can write this as n naught times 1 plus exponent minus h nu over kt plus exponent minus 2 h nu over kt plus exponent minus 3 h nu over kt, and so on. Now using the algebraic identity, 1 over 1 minus x equal 1 plus x squared plus x cubed, and so on. The above equation can be put into the form n equals n sub naught divided by 1 minus exponent minus h nu divided by kt. The total energy of harmonic oscillator can be obtained by first finding the total energy of oscillators in each elliptical strip and then summing over all the strips. In other words, multiplying equation 8 and equation 9 and summing over n, that is, E equals sum over the total number of strips, capital N sub n times capital E sub n. And if I substitute the values, expand this one equation, I can write this as n naught times 0 plus n naught times exponent minus h nu over kt times h nu plus n naught times exponent minus 2 h nu divided by kt times 2 h nu plus, and so on. Now this equation can be put into the form by taking n naught h nu exponent minus h nu over kt common from all the terms. It can be put into this one form. The sum of the term inside the bracket is in fact a series expansion of the form 1 plus 2 times x plus 3 times x squared, and so on, equals 1 over 1 minus x whole square. With this substitution, the relation for total energy becomes E equals n sub naught times h times nu times exponent minus h nu over kt divided by 1 minus exponent minus h nu over kt whole square. Now the average energy per oscillator can be obtained by putting equation 10 and equation 11 into equation A, which can be expressed as E sub AV equals n naught times h times nu exponents minus h nu over kt divided by 1 minus exponent minus h nu over kt whole square times 1 minus exponent h nu over kt divided by n naught. And this equation obviously straight away reduced to E average equals h nu divided by exponent minus h nu over kt minus 1. This is a very important equation and is known as Planck's distribution formula. From this, the average energy of oscillator as per the approach of equiposition theorem can straight away be obtained in the limit h tends to 0. Expanding the exponent and power series and setting the higher order of h equal to 0, we can write as h nu over kt exponent h nu over kt equals 1 plus h nu over kt plus order including square and greater than square, which obviously is equal to 1 plus h nu over kt. And from this we can, setting this value in the above equation, the average energy can be expressed as h nu divided by 1 plus h nu over kt minus 1, which of course reduced to kt, which is the classical energy obtained through equipartition theorem. Now the formula for the energy density can be obtained by combining equation 12 with the total number of moles. The number of moles Nm equals 8 pi nu squared divided by c cube d nu. So the energy density in the frequency range nu into nu plus d nu can be written as u of nu d nu equals 8 pi nu square divided by c cube times E average, which substituting the value of E average can be reduced to 8 pi nu square divided by c cube times h nu divided by exponent h nu over kt minus 1 times d nu. And this is, of course, the Planck's radiation formula. The only unknown and not directly measurable quantity in the above equation is h, which stands for the differential area of an ellipse. And its value was initially determined from fitting the data of the above equation with the experimental curve of blackbody radiation. It comes out to be 6.626 into 10 raised to power minus 34 joules seconds. Although the curve of blackbody radiation was successfully explained by this formula and a new regime of physics was discovered, however, nobody, including Planck himself, was convinced with the idea presented in equation 8, that is, En equals n times h times nu, because this goes against the perception of Maxwell electromagnetic theory, where energy is continuous function of the amplitude of oscillation and has nothing to do with the frequency of oscillations. Whereas in this equation, it not only depends on frequency, but is also discrete in terms of small n. Nevertheless, Planck might have no idea what a gigantic successor he had played, which expanded the boundaries of the playground beyond the limit of other age-mad physicists of his era.